When we talk about standard position trig, we really want to focus on the location, either location by angle, the angle description, or location by position, an XY coordinate. So we have 130 degrees here, and we want to draw this in standard position. It's important to recognize the quadrant that you're in. So we start at 0 degrees, that's our initial arm. We're at 90 at the top, 180, and 270 at the bottom. So 130 must be in quadrant 2. So quadrant 2, 130, somewhere around here. And that angle then represents our 130 degree rotation. And it locates that coordinate using the angle, but it also locates that same coordinate. We could also locate that same coordinate using an XY position. Okay, so we have our X and Y positioning here. And that forms a right triangle in which we can do our triangle trig. For 320 degrees, we have to go past 270. So we're going to again start our initial arm. We're going to go around, we're going to go past 270 and about 50 degrees past 270, maybe somewhere around there. And there is where our 320 degree rotation is going to get us. And again, we want to know that position. We could get there a different way. We could have gone in this direction. Okay, that would work as well. However, we're going to describe it with a 320 degrees, and again, we can describe that position with an angle, 320 degrees, or we can describe it with that X and Y coordinate, which again forms the right triangle for which we do our triangle trig. So this example here, it tells us the positioning with a coordinate. So at +4, -7, maybe somewhere around here. Okay, it's in quadrant 4. So I'm going to go over about +4, -7. And that gives us a location. And to find the radius, we're just going to use the X and Y positioning and Pythagoras. So we're going to do 7 squared plus 4 squared. So 7 squared is 49. Plus 4 squared is 16, so we're going to end up with 65. We're going to square root that, and we're going to keep the exact value length. Okay, if there's decimals involved, we can maybe use a decimal, but we're using whole number value, so we're going to keep our radical as a whole number value. So the radius is going to be √65. Okay, as a decimal value, we can work that out. So we're going to do √65 is going to be 8.06. Okay, but it's important to note that we're going to use this value. That's the value we want. That 8.06 is useful as a measurement, but we're not going to use that when we're writing out ratios. So when we go to our sine ratio, sine is always going to be the vertical. So we're going to use this y coordinate over the radius. Okay, the cosine is going to be the horizontal or the x coordinate. Cosine is +4 over √65, and tan will be the slope. We have negative slope, a rise of -7, a run of +4. Okay, and we can work out the decimal values of these as well. That's about -1.75. 4 divided by √65. So we're going to go 4 divided by √65. That gives us 0.496. 0 +0.496. Okay, so that means the horizontal length is about 50% the length of the hypotenuse. And then -7 divided by √65 is going to give us -0.868. So -0.868. 8. So about 87% of the length of the hypotenuse is going to be represented by that vertical y positioning. Okay, and in this case here, it doesn't ask for the angle, but let's solve for the angle anyways. We're going to do maybe an arctan. We could use either arcsine, arccos, or arctan. I'm going to use an arctan. I'm going to use the exact value. So when I do the arctan of -7/4, I end up with -60.26 degrees. Okay, and that angle is this angle in here. Again, that's not the angle in the triangle. It is a standard position angle. It's the angle that gets us to the position from the terminal, from the initial arm, moving in that direction.